Well friends, we know the big picture of the control system. The components of a control system are modeling, stability, analysis and design. So in model again there are two types of the model. One is a transfer function, usually called as a convention modeling. The second one is the modern modeling, which is nothing but the state space model or the state space analysis. So let us concentrate on the state space analysis now. So before going to look at the state space analysis, we will define some of the definitions which usually appear in a state variable analysis. The first one is state or state variable. So it is a minimum set of variables. Using the information of these variables at t is equal to t naught along with the information of the input at t is greater than or equal to t naught, then we can find the complete behavior of the system at t is greater than or equal to t naught, which means that this state variable gives the previous history of the system. For example, when I take a series RLC system, there are two variables, one is the inductor current and capacitor voltage are the state variables, and till t is t naught, what is the inductor current, how it is changed, and what is the voltage of the capacitor, how it is changed. So this information is nothing but my state variable information. So using this information and using the input that is applied, then we can easily predict the output behavior of the system at any point of the time t is greater than 0. So which is called the state of the system, and those variables are called state variables. Now state space. State space is n-dimensional space where the axes are the state variables. For example, in my system there are only two state variables, therefore it is a two-dimensional space vector. Look at here. So this is x1 and this is x2. So whatever the point we have, that point is having two coordinates, one is x1, other one is x2. Likewise, if you have n such state variables, then there will be a n-dimensional space which is called the state space. And similarly, take another one, the state trajectory. The state trajectory is the variation of the variables, state variables with respect to time in n-dimensional space vector. So in n-dimensional space, how the state variables are changing when time is independent variables. When you look at this graph, I have one point here. So this point, for example, I have two state variables. So this point at t is t naught, I have coordinates x1 comma x2. That means x1 value at t naught, x2 value at t naught will have a point like this. Then it will have the variation as the time is changing. At t is t of the final time, there is another point. At that point we have again x1 of tf and your x2 of the tf. So this variation is called the state trajectory. So not only this, we have the state response. The state response is with respect to time, you take any one variable and vary the variation. So if you, let us say I have x1 is one state variable, and with respect to time the x1 is varying like this. So this is called your state variation with respect to the time. Now these are the definitions we have. Now when you compare with its counterpart transfer function model, what are the advantages of the state space model? Let us look at what are the advantages. The first one is state space model is applicable for linear, non-linear, time varying, time invariant systems. Whereas when you compare with the transfer function is applicable for only LTI system, which means linear time invariant. Whereas here it is applicable for all type of systems. Next, the state space model is applicable for multi-input, multi-output systems, where the transfer function is applicable for only single input and single output systems. The another important advantage in state space is all the initial conditions are taken into account. So in state space model we have to take, let us I have inductor current. The previous inductor currents also will take when you are solving for the next time. So let us say T is T naught, we have inductor current, and after T naught, if you want to see what will be the value of the inductor current, how it is changing, then we have to take this history also. That is what the initial condition is. We are taking care of the initial conditions, where the transfer function we simply ignore the initial conditions. The another important advantage of a state space model is, if you have n dimensional system, if there is any n dimensional or nth order differential equation. So for nth order differential equation is converted into n first order differential equations, and the solution for the first order differential equation is very easy. In fact, this is the motive to develop the state space model. So let us say I have a 10th order system, the convert the 10th order into 10 first orders. Therefore, each first order will be the one state variable. Then we can easily find out all 10 state solutions. So this way we can easily find the solution of the system. So very important point in state space model is nth order differential equation is converted into n first order differential equations. Therefore the solution becomes very easy. Then when you look at the next advantage, now in state space, along with the information of input and output, the information of the intermediate signals also we can obtain. The intermediate signals are the states of the system. For example, if you take RLC system, so input is voltage and output is a capacitor voltage. So supply voltage, capacitor voltage. When you look at the transfer function gives the relation between the output capacitor voltage to input supply voltage. In between, if you want to know what is the inductor current, it is not possible. Whereas in state space, I can assume or I can take the inductor current is one of the state variable, then I can find out the solution of that state variable. So intermediate signals are possible in state space model. Similarly, your state space model, we will use all matrices. Therefore, for any complex systems, then we can use the help of the digital computer or a microprocessor to solve the system equations. Now again, there are certain drawbacks with the state space analysis. The first foremost drawback is the state space representation is not unique. That means if you have any physical system, you can write your own representation, you can have your own model with you. A transfer function is not like that. Whatever the method you use, but the final transfer function will be same. It is not the case with the state space model. The another is when you coming to the design, the state space model, the design of controllers is a bit difficult and complex in state space model. What is the state model? Basically, state model has two equations. The first equation is called the state equation, and the second equation is called the output equation. So state equation, output equation combinedly we call it as a state model. So in transfer function we have only one equation, output is equal to, let us say I have the G is the transfer function, input is R of S, output is C of S. I can write C of S is G of S into R of S, that's it, only one equation. But in this case we have two equations. Let us look at the first equation, which is the state equation. Then how can you write the equation? X dot is equal to AX plus BU. X dot is AX plus BU. So this dot indicates the first derivative. X dot means dx by dt. Now this x dot is a state vector. In fact, it is a derivative of the state vector. This state vector has so many number of state variables, and the number of state variable depends on the order of the system. When you write a differential equation, then if it is a third order, then the state variables, number of state variable is 3. And also the number of state variables, we can also say that depends on number of storage elements that are available in the system. So for each storage element, if you have storage element, then only there will be a dynamic variation of the variable value. So with that I can give the state, because state means there must be some variation. Now, so this is the state vector x dot, differentiation of the first derivative of the state vector is A. What is A? A is the system matrix or the state matrix. The system matrix is very important in the state model. And what is X? X, I said, it is a state variable. It is a state vector consisting of all state variables. B is the input matrix, U is the input vector. So vector will have only values u1, u2, u3, whereas a matrix will have all the elements, both columns and all the columns and rows. Now, so when you look at the dimensionality, let us say it's a nth order system, then what is the dimension of x dot? The dimension of x dot is n cross 1, means there are n number of variables, it is going to be a vector. What is A? A matrix dimension is n cross n, where n is the order. Again, what is x? X is also n cross 1. Then what is u? Let us say there are m number of inputs. Number of inputs are m, because state space model is applicable for multi-input, multi-output system. I can have any number of inputs. For example, the number of inputs is m. So u is m cross 1. Then what is the B matrix now? N cross m. So n cross m is a B matrix, and m cross 1 is u, and x is n cross 1, a is n cross n, and x dot is n cross n. So this is nothing but my state equation. Similarly, I can write the output equation. The output equation is y is equal to cx plus d. Y is output variable and the CDR matrix. C is called the output matrix, and x is, of course, we know it is a state vector, and d is the transformation matrix. Transformation matrix gives the direct relation between input and output, and u is, of course, it is input vector. Look at the dimensionality. So let us say there are p number of outputs. Number of output is p. Then what is this y vector? It is as p cross 1. And what is x? X we know it is n cross p. Therefore, obviously the dimension for the C matrix is going to be p cross n. And d we have u is m number of inputs we have. Therefore, m cross n. The number of output is p cross n. Therefore, D matrix is going to be p cross m. So this is a complete dimensionality. So state model means you have two equations. One is the state equation, other one is output equation. We have seen these two equations combinedly we call the state model or state space representation. When you look at representation this way, so this is my MIMO, that is multi-input multi-output system. So there are set of inputs available, multi-inputs. So these inputs are like this. Assume there are m number of inputs as I just seen, and there are set of outputs. Those outputs are p number of outputs. And now, as I said, intermediate signals also we can take from the system. Those intermediate signals are the states. Then how many number of states? M number. It depends on the order of the system. So n states, m inputs and p outputs. Now using two equations, then I can draw a block diagram like this for the state space model representation. Now how can you draw this? So first of all, I am going to take one integrator or set of integrators, because the multi-input multi-output system, the output of the integrator is a state vector, input to the integrator is the derivative of the state vector. So x dot here before the integrator, after the integrator x. Now I have a feedback like this with a matrix A, and this feedback is not the negative feedback. This block diagram is not the control system block diagram. It is a representation of the state variable, state model. So I have place. Now input is u. So for this input I have one more matrix B. So u, B, and it is given to summing point. And I am taking one more from the input I have D, and from D I have one more summing point here, and for this summing point one input is from U, other input is from X into C, and when you add these two then you will be getting Y. So you can write the equation from this block diagram. What is Y? C into X plus U into D. What is X dot? X dot is X into A, and also we have B into U. Two equations, you can model it and you can represent like this.